Hello everyone, I'm Sita Zhang from LightTrans International. And in this talk, I'm going to introduce you VirtualLab Fusion, a physics optics simulation platform. LightTrans is located in Jena, in center of Germany, and I'd like to introduce our teams first. So LightTrans is founded in 1999, and together with its partner company Photonics, and together with the Applied Computational Optics Group of the University of Jena, we provide different and various optical technologies for optical modeling and simulation. Additionally, LightTrans is also responsible for technical support, trainings, and engineer projects, which is based on the software VirtualLab Fusion. Now, VirtualLab Fusion is a physics optics based simulation platform, and it has been used by different users from industry, from universities, from research institute all over the world. Now, if we talk about physics optics modeling, what we mean is to solve Maxwell equations for the whole system. But VirtualLab is not a single solver software. It's not like those finite element method or finite difference time domain method. It is a platform. It's a platform that contains different methods on board. What I mean by that, let's just take some examples. If we consider, for example, a complicated modern optics system, you might find different types of content, like lenses, prisms, gratings, micro and nanostructures, fibers, and so on. And for each types of components, there might be a corresponding efficient and also suitable solver for these kind of cases. That's exactly the basic idea of VirtualLab. So as shown on the right side, we have a collection of few solvers, or let's call it Maxwell solvers. Each of them corresponds to a particular situation which one might have in a complicated system. And for each of them, we develop a particular, or let's say several kinds of particular solvers. And we use these solvers in combination for the whole system. Therefore, it allows an efficient and feasible simulation, which is based on the solution of Maxwell equation, but for the whole system. Now, here we have an overview of our software products. VirtualLab Fusion is the basic platform, and it has been divided into basic and advanced versions with different capabilities. In addition to VirtualLab Fusion, the basic platform, we have, for example, the diffractive optics toolbox and light guide toolbox, and so on. These toolboxes are used for, as their name says, for particular applications like diffractive optics element analysis and design, or the design of a light guide system. Now in this talk, I will go through several of these important and selected features for VirtualLab software, and I will also show particular examples with respect to these features, explain how it works in the software. The first topic I selected is laser beam optics, and let's have a look by using an example and see how VirtualLab could help with the modeling and design of laser beam optics systems. So the first example I selected here is the analysis and design of a Afocal system for laser guide stars. Now let's have a look at the task. So this is a task that we found and we followed from a published literature from Mr. Clement. So where he discussed about the design of a laser guide star applications. So it doesn't really look, a system doesn't look so complicated. It's just one laser source, which is modeled by a fundamental Gaussian, and then you have two subsequent lenses. The two lenses are constructed in a way that the distance between them equals to the sum of their focal lengths. So it makes a focal system. But you must be careful that this laser guide star is used to illuminate somewhere which is super far away from your system. So it's going to be used to generate a spot far away in a space. And here, just take an example, it can be 10 kilometers away from the system. And for such laser system, it's important to take all the beam optics properties into consideration. For example, the possible diffraction effects for laser beams. And you must do it very, very carefully. You must do it precisely because you want to control your beam at a very far distance. So let's have a look at what we have here. Let's take an example of geometric optics. Assume that if you are going to use geometric optics to predict the performance of this system, well, obviously it is a simple magnification system, and if you calculate the ratio between the focal length of lens 1 and lens 2, you get a ratio, a magnification ratio, and by that you can predict that the beam afterwards will have a diameter of 16.7 millimeter. And geometric optics doesn't predict any change of the beam diameter after the second lens. So it means that it will tell you after 10 kilometers you will have a beam diameter of 16.7 millimeter. Well, that sounds not bad, not quite good. But that's not the truth. That's not truth if you consider the possible diffraction effect of the Gaussian beam. Although this is a very small effect, but it might develop over a long distance, right? So let's have a look. If we perform a physical optics-based modeling of this simple system, then at a target plane at 10 kilometers away from the second lens, then you are going to get a Gaussian beam. You still see a Gaussian beam here. By the way, this is exactly the simulation result which we got from VirtualLab, and it predicts a beam diameter of over 400 millimeter. That is much larger than what you see from the geometric optics prediction. And obviously for such cases, if you want to take the diffraction effect of a laser beam into consideration properly, you must work with physical optics. And it is the same for the design of such systems. You cannot just use geometric optics to try to optimize such a Afocal system for laser beam, for guide star. It doesn't work. You must consider the diffraction effect in your design procedure. And here is an example of what we did. So we use fully physical optics simulation engine in our software and use that together with a parametric optimization, that is downhill simplex method. We set the initial focal length for first and second lens, and then we try to we vary them. And then we try to see, okay, what is the minimum spot diameter that we can get at 10 kilometers away? Well, obviously we want to get a very bright and strong spot in a space. First, we make a test with the input beam width of 250 micrometer. And by that, we get the minimum diameter at 10 kilometers away, at which is 116.4 millimeter. We try another one. So for example, now we increase the input beam diameter to 1.5 millimeter. Again, we are varying the focal lenses of lens 1 and lens 2 freely, and we try to minimize the spot diameter at 10 kilometers away. Now we get the same value, it's still 116.4 millimeter. we can try more input values and you try to optimize the system. You get the same minimum spot diameter at the end. So, is this the truth? So we compare the result with the theoretical analysis from Mr. Clement, and he's shown that theoretically the minimum beam radius at the target is 58.2 millimeter. So this can be shown for any simple Afocal system. Just compare our result with theirs. Well, we are showing the diameter value, therefore we are twice of the radius values shown by Clement, but otherwise we have a very good agreement between the theory and our numerical simulation. Because in our simulation, we have taken the diffraction effect of the beam into consideration rigorously. So that's why we get a very, very good agreement between the simulation, numerically, and the theoretical derivation. Okay, that's just one example on laser beam optics. And in addition to that, we have more examples from our website. For example, you can build up a 4F spatial filter to clean up your beam. You can evaluate a laser scanning system in 3D space with a f-theta lens. We can collimate and focus a laser beam. Even more, we can modeling the generation of more complicated laser beams like Basel beam or Airy beam. And VirtualLab can also used not only just for CW laser, but can also be used for ultra-short pulses together with gratings. So these are all possible applications for VirtualLab on laser beam optics. Now I like to move to the next topic, imaging optics. So let's say the field of the traditional ray tracing optics software. So what we can do and what we can do more here. I selected one interesting example according to Aber's theory of image formation. So we are not using a very complicated lens system, but in this case, we just used one aspherical lens and one spherical lens. But in front of that, we placed a chromium grating in front in the object plane, and we use this as a test object. We want to use this grating together with our lens systems and show how the image formation process can be simulated in our software. So here again we are using a Gaussian beam which models a laser beam. Now this is an example of what we can see in VirtualLab simulation. The first thing you can see is that if you illuminate a grating, a chromium grating with a laser beam, you can directly see the field behind this object. And here you are seeing this altering, changing bright and dark stripes. Well, here we are using a chromium grating. And after that, this diffraction order will go through the aspherical lens, and at any plane in the system, you can check the performance. For example, in this case, we select to observe the result at a Fourier plane, which is the bifocal plane of the first aspherical lens. And here we see the distribution of different diffraction orders. Well, as is well known that you have a very strong zeros diffraction order and the minus first order. But the second order, you see that is obviously darker. Well, just want to mention that in our simulation, the grating can be modeled rigorously by using the RCWA method. And therefore, we have exact access to the grating diffraction efficiencies. And here in the Fourier plane, you are seeing the brightness of the spots according to the diffraction efficiencies. Alright, afterwards, each of these diffraction orders goes through the second spherical lens, and at the end, on the image plane, they make interference pattern. That gives you the image of the grating. In VirtualLab, you can also make arbitrary post-analysis of your simulation result. So all these results I'm showing here are generated in VirtualLab. So I get the image behind the greeting object. I get image behind. I get the greeting image at the end, and I can again make a profile line on each 2D images. I can extract the result and analyze them in detail. In this case, I just make a distance measurement, and you can see the magnification is 10 times according to my design. Alright, in the next case, I'm making the system a little bit more complicated, like in the upper series, how he shows the resolution limit. In comparison to the previous case, an additional aperture has been placed on the Fourier plane, that is a bifocal plane of the first lens, and I let the aperture of the aperture, the diameter of the aperture variable. Now in the first case, we keep the aperture width at 5 mm, which is a relatively large one, and we can see that diffraction orders from -4 to +4 order go through the system. They contribute to the final image and makes a very good, well-resolved result. Now I change the width of the aperture and make it a bit smaller. Now in this case, you don't have so many diffraction orders going through. You just have diffraction orders from -second to +2nd order. I blocked those higher diffraction orders. And in this case, you still see, with contribution of these 5 orders, you can still see the period of this grating at the image plane. But obviously, it's not really sharp. You see a kind of smoothed image of the grating. If we do it even more, I reduce the size of the aperture to just 1 mm, and then it's gonna truncate also the -first and plus first order. They're just partially truncated, so some of this plus minus first order can still go through, and therefore you can see, although it's a very blurred image, but you still see the periodic change. At last, if you make your aperture so small that only the 0th diffraction order, that is the normal order, goes through the system, then finally what you see in the image plane is just a magnified Gaussian beam. There's no image at all. And this is exactly what you can learn from Abel theory. And in this system, you see that we can combine use of different kind of technologies. We use solvers for lenses, we use solvers for apertures, we have solvers for gratings. And in this case, especially, we are using a RCWA rigorous solver for our gratings. And we have the coherence of the light under control. Finally, we are making a coherent summation of different diffraction beams, and we make the image. So there are some more examples on imaging optics in VirtualLab. For example, we have the well-known Debye-Wolf integral included and implemented in our software. So that's a typical tool people want to use for analyzing the idealized imaging situation for a microscope. And you can analyze, for example, chromatic effect in microscope. In VirtualLab, we always use vectorial representation of light. Therefore, it's also very convenient to study the focusing effect of a polarized beam. Of course, you can investigate the resolution of a microscope by using Rayleigh criteria as well. And there are also advanced type of microscope like Fourier microscope that you can also build up in VirtualLab. Next example I selected here is for interferometric systems. And I'd like to show how you can build up such a system in VirtualLab as well. The example we use here is a collimation testing with sharing interferometry. So in this system, we first used an objective lens together with a spherical lens together to make a beam expansion and collimation system. The input beam has a relatively small diameter, 1 mm, and after this beam expansion, we can get probably a beam diameter as large as 25 mm, the same as the diameter of the second lens. Now the question is that in practice, how you like to check the quality of the beam collimation. One typical way is to use a so-called shearing interferometry. And the setup is very easy. It's just you take the use of a shear plate, which is almost a parallel plane, but with a small wedge angle. In this case, we have a small wedge angle of 0.015 degree. We first analyzed the performance of the collimation lens system. Obviously, you must tune the system in a way that the distance between the two lenses are corresponding to the sum of the focal length, so that you can get a constant output wavefront. And in this case, in VirtualLab, we have found out that by simulation, we can check the wavefront. And in this case, we checked out that at 448.2 mm, we get a perfect collimation. At this position, we have a plane output wavefront that corresponds to a collimated beam. Well, then let's put the shear plate behind the collimation system and check the interference. If you keep the distance between the two lenses as 448.2 mm, where you have a perfect output wavefront, in this case, you are going to see that the interference fringe appears in the orthogonal direction with respect to the shearing direction. So in this case, you have two beams going away from each other along x direction. This is the shearing direction. And perpendicular to that, you have the interference fringe. If you change the distance between the two lenses, let's make it smaller, or let's make it a little bit larger, then you're going to see the rotation of the interference fringe. You're still seeing them parallel, but they are no longer orthogonal to the shearing direction. And this is exactly a well-known effect and a practical way to test the quality of beam collimation. All of these are simulated with VirtualLab. So there are some more examples on interferometric systems, like the typical Michelson interferometer you can build up easily. You can also build up, let's say, some more advanced system based on Michelson, like the coherence measurement or a coherence scanning interferometry based on Michelson. You can also use interferometric setup to generate, for example, spatially varying polarizations. For example, here we have an example with Mach-Zehnder interferometer. And also, typically, we have the Phison interferometer for optical testing, which is the most typically used type of interferometer in the industry. Alright, next topic I'd like to show you here is about grating analysis, which is exclusively included in VirtualLab Fusion Advanced version. In VirtualLab, we have the rigorous RCWA or fully mono method, FMM method included for grating analysis. And in one of our recent releases, we have enabled the modeling and design of metagratings. And here we have selected one example about the modeling and design of a blazed metagrating. This example is selected according to the work of Philippe Lalande about 20 years ago. So this is one of the pioneer works in this field. And here the author has selected square pillars to make up a blazed metagrating. Now, first of all, we want to have a rigorous analysis of the nanopillars. According to the literature, we selected the unit cell of the pillar to 380 nanometer, the height of pillars to 545 nanometer. And here we are going to vary the diameter of the pillars and see how it works. By the way, here we have used a titanium dioxide to make the pillar because it has a relatively high refract index at the visible range. Now on the right side, you see the simulation result, rigorous simulation result from VirtualLab. The red curve shows the phase transformation. Let's look at the range within, let's say, the first 300 nanometer. The red curve covers almost a 2 pi range, and the black curve, which represents the efficiency, it is almost constant and high, except at some particular resonant locations. Next, we are going to select those proper pillar diameters and distribute them on the meta surface plane. And here we have selected, according to Philip Long, we have selected 5 different values of our nanopillars. If you look at this red curve again, you see that if you have a relatively small pillar diameter, it corresponds to a relatively small value of phase transformation and vice versa. Therefore, if you want to make a blaze grating, you won't have a linear phase transformation. So we have selected 5 pillar diameters, which generates almost evenly 5 different phase values within 0 to 2 pi. And we distribute them on the meta surface in a sequence way. Now, after constructing the whole meta surface, we can put these 5 pillars again into one period. That makes the period of the metagrating. And again, we are going to use the rigorous RCWA method to model this structure. And by that, we got a quite good diffraction efficiency result. So here you see that for both TE and TM polarization, this metagrating show a quite high diffraction efficiency for both polarizations. And on average, you get 77% diffraction efficiency in the first order. But that is not yet the optimized result. For example, it's known that when you make up these metagratings, there's still space to optimize it. Therefore, we choose to vary the pillar heights, the pillar positions, and pillar diameters. And here you can see, by using RCWA as a kernel and together with the downhill simplex optimization, we can further increase the diffraction efficiency from about 77% to over 85%. Now here we're just showing the result before and after the optimization as a comparison. There are more examples on grating analysis which can be done in VirtualLab. For example, you can analyze a nanowire grid polarizer, or you can design optimized slanted grating, which are nowadays very often used for AR display. You can design polarization-independent transformation gratings, or there are special type of gratings like the resonant waveguide grating and parity time symmetry gratings. So next, I also like to mention we have a special toolbox, Diffract Optics Toolbox, which is used for DOE design or diffract lens HOE simulation. Very briefly, for example, you can design a beam splitter which is generating a particular pattern according to your needs, like here. Or you can use this toolbox to design and model a diffractive lens. For example, in this case, we show an intraocular diffractive lens. Last but not least, I would like to mention our light guide toolbox, which is particularly designed for light guide modeling and light guide design, which is probably the first software which can do that in the world. Now, here's just an example where you can show a kind of a traditional type of light guide according to Levola. Or you can also design and model this kind of new type of light guide structure with using 2D gratings for EPE and outcoupling like shown here. And finally, I'd like to come back to our basic concept, connecting Maxwell solvers. And based on this concept, VirtualLab enables modeling and design of various types of optical systems. And if you have any questions, please feel free to contact us, contact LabTrans, visit our website, and thank you for listening.